Hello, class. Today we're going to be talking about psychophysics. This is chapter 4 in your Hunt text, so we're skipping ahead a few chapters and moving ahead several centuries to this very unique period of time in the history of science that came right before the founding of the first psychological laboratory in 1879. So we're not talking about Europe or, North America or Asia or Africa. This lecture places us firmly and squarely in Europe. And we're going to begin with several characters, some of them interesting, some of them controversial, but all of them in some way contributed to the discipline of psychology through the years. We're going to start with a very controversial character named Franz Anton Mesmer. So these are his dates, 1734 through 1815. It may appear to you to be kind of a minor point that he was a society physician in Vienna. Vienna may not matter to you very much, and I'm sure most of you have heard of it, but to understand Vienna during this era, this is the height of the Habsburg Empire and the Austro-Hungarian Empire, of course run by the Habsburg family. So when we say Vienna, we are talking about a place of extreme central importance at the time, far more important than, say, a place like New York City, and arguably even a more influential place than some place like London or maybe even Paris. Vienna still remains a city that has largely bridged the gap between Eastern and Western Europe. And because of all the wealth and the power and the influence of the Austro-Hungarian Empire, this was really the place to see and be seen. So Mesmer proposed a couple of ideas and probably became most famous for some of his infamous works, but came to believe, and it's hard to tell how much he really believed this himself or if he was just a total charlatan, but he believed that that magnets could realign a sick body, that because there is electrical energy inside of people, then it's possible that electromagnetism could affect people, and therefore the application of magnets he thought could balance people out or align people. Now again, whether he believed this or not is hardly the point. The point is that he was able to convince a lot of his patients throughout the years that he knew exactly what he was talking about. He plagiarized his dissertation, earning his degree, and in it he asserted that planetary motion affects bodily fluids and therefore health. So the idea here is that the gravitational pull, say, of the moon, which is strong enough to influence the tides, would certainly have something to say about the fluids within your body. This is not true, but he nevertheless made a pretty compelling case. And to understand the era, too, you also have to understand cafe culture, that the way word spread in Mesmer's day was via the cafes. If you've ever been to Vienna, it's a really neat thing to go and experience one of these old vintage cafes. They've been around for several hundred years. This is a picture I took with several of my students at Café Central in Vienna several years ago. And most famously, the Café Spirl, which is the cafe that Sigmund Freud spent a lot of his hours, day in and day out. And that's a picture I took of my coffee that I got there. I think, actually, no, that one doesn't look like my picture. I think that's one that I downloaded. But anyway, I did have a nice meal there. Here's Mesmer being depicted in film and in art, wearing this big, very theatrical costume and usually being surrounded by very histrionic and easily gullible, wealthy, and naive women. And he earned his reputation by curing people and using various skeptical methods. But of course, most people were influenced not by actual medical healing, but by the placebo effect. So why do we even talk about somebody like Mesmer in this context? Well, because whether Mesmer was advocating something totally nonsensical and false, or whether there was some grain of truth to it, the idea was that he believed that there was a physical cause and effect that was taking place inside of a person's body that could affect their mood and even their health. So we have to discuss Mesmer, even if most of his work was the work of an imposter. He believed that magnet treatment could treat any malady because of these principles of gravity that we'd already talked about, planetary motion and the like. What we do now know is what I said just a moment ago, that most of his patients were actually quite hysterical. They suffered from, say, histrionic disorder. They were easily gullible. You could talk them into just about anything. And so they were responding really to the placebo effect, or the power of suggestion. Later, he abandoned this idea that gravity causes these changes, and then changed his mind to believe that magnetism, not gravity, was the key to health. And that's when he started applying magnets to people's body, and he would tell them that they were getting better, and many of them complied and actually got better. However, after he once claimed that this magnetism successfully treated a blind woman, when it was found out that she eventually, the temporary healing that she got from her blindness went away, it caused a major scandal, and he fled to another city where there was lots of wealthy, gullible people, Paris. While he was in Paris, he switched his focus once again and believed that he himself, his personality, tended to be the source of his power, and it was he, as this kind of cult of personality character, that generated these responses in patients. He came to believe that he must have had some unusual amount of magnetic power, and his approach became known as mesmerism, from which we get the word mesmerized. The key is that Mesmer himself believed that it worked, even if he deep down thought that he was an imposter. He himself genuinely was able to convey that he believed it, and therefore his patients came to believe it as well. Several investigators, including Benjamin Franklin, were invited by Mesmer to investigate his claims, came to the conclusion that he was a complete fraud. And so this idea of pure mesmerism has really been in disrepute ever since, and now is relegated to the stuff you see in traveling circuses and carnivals. But it did raise this very important question. What is this placebo effect? And is it powerful? Well, as we know, as you probably know by now, the placebo effect is very powerful. The ability of the mind to come to believe something that's not true, but nevertheless believe it enough to where it actually causes a powerful and significant treatment effect. James Braid, a physician in Scotland, later called hypnosis, as it became to be known, as neurohypnology, and then later hypnosis, which literally translates into nerve sleep. Auguste Libaud from France was probably the most famous practitioner of hypnosis, and he was the one that said, among other things, you kind of get this stuff from movies, like, look into my eyes, you're getting sleepy, I'm going to suggest something, and then when you wake up, or when I count to 3, or when I snap my fingers, you'll remember nothing, but you'll do this. So these the kind of stereotypes you see about hypnotic behavior that would show up in literature and in movies, that was Libaud from France. Continuing, the most famous and probably reputable practitioner of hypnosis, before Sigmund Freud, who did use hypnosis pretty regularly, was Jean-Martin Charcot, who worked at the famous hospital, the Salpêtrière, in Paris, a hospital that still exists. Incidentally, that is the hospital where Princess Diana was taken after her car accident and her ultimate death. It's right there in the middle of Paris, and is a hospital with a sterling reputation. And back in this time, it was famous also for treating psychiatric patients. And so Charcot was he wasn't the director of the Salpêtrière as far as I know, but I think he was chief of psychiatry, and developed a reputation as being the most influential hypnotist ever. He also, today we remember Charcot less for his original work in hypnosis, and we mainly remember him as being someone who trained Sigmund Freud in the art of hypnosis, and originally believed that only hysterical patients could respond to hypnosis. And it's not entirely true. We now know that hypnosis mainly works on people who tend to be a little bit more gullible, who tend to have a more vivid imagination, and have the ability to, I don't know if you've ever had this feeling, but when you've watched a movie and you feel like you're really in the movie and you completely forget where you are, if you're the kind of person who really gets into a story and you almost lose all track of reality, or if you're the kind of person who drives somewhere and doesn't realize that you've made it to your destination until you've made it to your destination, and you realize that the entire trip you were thinking about something so deeply you didn't even notice that you were driving. Those types of people tend to be more prone to hypnosis. But he believed that only hysterics could respond. The success of hypnosis is now attributed more to patient variables and their own motivation, not necessarily neurological functioning, but at least this was a start in the belief that something physical was causing something mental. So moving along now from hypnosis to physiognomy and phrenology. Now we're really starting to run right up against the very beginnings of psychology. This was another ill-fated attempt to try to link physical variables with mental variables. So physiognomy refers to interpreting personality and mental functions due to facial features. So sometimes people who practiced physiognomy believed that if you had a large forehead or a small forehead, that meant a certain type of intelligence. Phrenology is when you interpret a person's personality and mental functions due to different shapes and bumps on the skull. So if a skull was thought to be not proportional, or one side was bigger than the other, or there were several bulges in the skull, it was thought to be linked to certain aspects of the personality. At one time, these fields of physiognomy and phrenology were thought to be the great cutting edge of science. Currently, they're little more than the butt of jokes as we look back and say, what were they thinking? Lots of methodological flaws, lots of really shoddy research was done. Today we have far more advanced research methods that people back then just didn't apply. But the main thing to remember here is I don't want you to look back on this and make fun of it. I want you to recognize that for many, many people, this was a very, very serious endeavor. And perhaps most importantly for our purposes, it was the first really serious link to try to link, or first serious attempt to try to link physical aspects of a person's body to their mental functioning. Next, the most famous phrenologist of them all was a guy named Franz Joseph Gall. We can't only talk about him as a phrenologist, though, because he did a little bit more. So these are his dates, 1758 through 1828. As I said, he was a very famous phrenologist, but in his own right, he was a very accomplished neurologist. Among other things, he made this amazing discovery of contralateral brain function. That means that when you are moving your left hand, it's the right hemisphere that's controlling the movement of your left hand, and so on and so forth. So this idea that one hemisphere controls many of the behaviors that you perform on the contralateral side of your body was the discovery of Gall. He also discovered something that is generally true, and that is the larger your cerebral cortex, the higher your intelligence. So it's another way of saying that the more dedicated cortical space you have, there tends to be a mild correlation with higher levels of intelligence. What Gall hypothesized with phrenology, because he did find that larger cortices, a larger cortex, linked to higher intelligence, he believed that the larger your cortex was, because there was no space inside the head for larger cortex to grow, he believed that this forced the skull to bulge out. So parts of the cortex would push the skull outward in those areas, and especially in those areas where people were strong. So for example, he believed people with large eyes had a really good memory, and that's because the memory areas would push up against the eyes and bulge them out a little bit. It was an interesting idea, but we now know that a larger cortex does not push against the skull. The skull is typically fixed in its course of development. Although the skull does change size as a human being grows, what changes it is not the cortex pushing out against it. The main problem methodologically that Gall had is confirmation bias. He only looked at patients who fit his hypothesis, and he ignored patients who didn't fit it. So that's a great psychological term for those of you who are looking to take the psychology GRE someday. That's a question that's often on the psychology GRE. What is the confirmation bias? It's the tendency for people to only look at information that confirms their hypotheses, but then also to ignore information or evidence that would disconfirm their hypotheses. So it's an error of reasoning and judgment. He also didn't engage in random sampling, which meant that the people who participated in his study did not have an equal chance of either saying yes to being included or being said no to being excluded. You may have heard of phrenology before, maybe not, but most of you have probably seen one of these diagrams before that shows a cranium and then the different things that it's responsible for. This is largely not true, although again, the idea here doesn't really have anything to do with the truthfulness or the falsehood of this diagram, but the fact that people were making a serious attempt to try to map functions of the brain. We do know that there are several specific functions linked to certain areas of the brain. Those tend to be overstated, but there are some. And that's what's most important here, is that a historical movement, this was a really interesting time to be alive. Pierre Flourens, a French physiologist, once excised the cortex in animals to see if their behavior changed in accordance to Gall's theory. Well, as it turns out, they didn't. And so a lot of what Gall was talking about was kind of disproved. What Flourens found is what we now know today to be true, which is that most brain functioning is not localized in one specific isolated area, but is distributed like a network throughout the brain. But nevertheless, that mistake that Gall made nevertheless led to some of the first really comprehensive and well-done brain experiments, which led to the discovery of Broca's area, named for the researcher who found it, and Wernicke's area, also named for the researcher who found it. And both of these areas, in the frontal lobe and in the temporal lobe, respectively, have to do with language production and language comprehension. Broca's area is responsible for language production, producing speech, and Wernicke's area is responsible for language comprehension, understanding the meaning of words. Those are two of the few examples where there is a highly specified function for a particular region of the brain. So a lot of people, right before the field of psychology started, were already beginning to be interested in emotions and memory and cognitive functions and things like this. And as far as purely psychological questions, philosophy had taken psychology about as far as it could go. Physiology became, in the mid-1800s to the late 1800s, a really powerful force in the sciences, and people began to pay very close attention to how physiology related to human behavior. Also, because this interest also happened at around the same time that our ability to measure things also advanced. So transportation advanced, manufacturing advanced, both large and small. The quality of the instruments that we had at our disposal really improved. And also there was this, just in the 19th century, there was this big obsession around the world with trying to measure accurately as many things as possible, from the tops of the highest mountains to the depths of the deepest part of the ocean, to the limits of human behavior, like how long can you hold your breath, or how many things can you remember in 5 seconds. People were really interested in testing these limits. So this cultural zeitgeist of having a lot of interest in the sciences, plus the interest in human behavior, plus the interest of physiology, plus the technological advancements, it led to this really fertile time in the history of sciences when psychology was soon to be given its birth date. So the first great physiologists that we'll discover here, they provided the immediate foundation to Wilhelm Wundt. Wilhelm Wundt is the name of the German psychology professor at the University of Leipzig, who founded the first psychological laboratory in 1879. So the first person we'll talk about here in that context is Johann Müller. Müller, those are his dates, 1801 through 1858. His most famous discovery was something called nerve specificity theory. See, the reason why this was a significant discovery is because it was once thought that all of the nerves we have in our body fire for all stimuli based on the characteristics of the stimulus. So, like, for example, it was thought that the stronger the stimulus, the stronger we would fire. So if there was a bright light that came on, then our nerves would really fire for a bright light, but not very strongly if the light was dim. Or if there were a loud sound that was being produced by someone, say, singing a song, the louder they sang, it was thought that our nerves would fire more vigorously and with more energy. What Mueller found was, no, these nerves there are specific nerves in the brain and in the central nervous system that will fire for specific pieces of data. It's not a matter of how strongly they fire, it's a matter of which nerves will fire and which ones will not. So that was called nerve specificity theory. So he discovered, for example, that optic nerves encode only visual stimuli. And so then that led to a further question. Do these specific nerves then determine the quality of the environmental stimuli? No. He actually found that there was even a different set of nerves that actually caused us to perceive environmental stimuli as being a certain way, and that was what's called the association cortex. So if you're only processing visual information, That's the main cortical area. But if you're trying to process the quality of that, that was the responsibility of what he called association cortex. Mueller also told us that our brains do not contain small pictures of reality. Rather, our nerve impulses give us analogs of reality. This is one of the more famous questions in the history of philosophy and science, and that's the homunculus question. Homunculus is Homunculus, homunculus. Homunculus is the idea that inside of our brains, we all perceive there to be a kind of little person who's in there, who is taking all the information in, and that when we try to remember something or think about a particular subject, we think about something that is not unlike a TV screen that has almost like a videotape of things that happened in the past that keeps on playing for us. And in reality, of course, there is no homunculus in the brain. There is no TV screen in the brain. What tricks us into thinking there's something like that in our brain is just a particular pattern of nerves firing in a certain way. They give us something that's analogous to reality, but we don't have a picture-perfect recreation of the things that we've seen in our brain. It only looks like that. So Mueller said that we don't actually see objective reality and interpret it as such. Rather, our senses receive bits of information in the form of electrical nerve impulses that fire for specific pieces of information. And then somehow, and this is the part that is like a TV screen, we somehow put all of that information together in a way that makes sense. Now, Mueller was not perfect. He didn't get all of his ideas correct. But in these other areas about nerve specificity theory and things like this, he made tremendous discoveries and pushed the field really far forward. As we continue now, we're going to switch over to Psychophysics Part 2, which is a different set of slides for you. The next person we'll talk about is Ernst Weber. Weber, those are his dates, 1879 through 1878, so a little bit younger than Mueller, but I'm sorry, a little bit older than Mueller, but also outlived him by several years. Weber was at the University of Leipzig, so that same university in the former East Germany, where Wilhelm Wundt was. And Weber's interest was in studying different types of sensation in different parts of the body. And what he was really interested in was, how can we tell, because we can, he noticed this, that we were all able to do this, how can we tell in our brains that a certain stimulus has that we've perceived it or sensed it with a certain degree of intensity. Like, for example, if I came up and greeted you gently by putting my hand on your shoulder and saying, "Hey, how are you doing?" you would feel my hand on your shoulder. But what if I came up to you and slapped you on the back really hard and said, "Hey, man, how the heck are you?" and it kind of hurt you a little bit. You could tell the difference between the first greeting and the second greeting. Well, what Weber was wondering is, how? How can you tell the difference? I mean, we both know that we did try harder. We applied more pressure in the second greeting than we did in the first greeting. I mean, we practically hit the person in the second greeting. But how does our brain make sense of that? How does our brain know that we can tell the difference between the first greeting and the second greeting? And as it turns out, the brain has a very precise way of doing this. His big question was really, how do we detect differences in the strength of stimuli? So, for example, if I pick up a 50-pound weight, how can I tell that it's heavier than a 60-pound weight? Well, you might say, well, anybody could tell the difference between those two weights. Somebody else might say, well, I can pick up a 50-pound weight, but I can't pick up a 60-pound weight. Okay, that's all fine. But really, is there a point at which the differences between two stimuli are so small that you really can't tell the difference between them at all? Well, that little tiny precise difference is called the just noticeable difference. It has a name. The just noticeable difference, or the JND, is the minimal amount one stimulus must differ from another stimulus for us to detect it at least 50% of the time. So if I said that, if I showed you that there's a 100-pound weight and a 99-pound weight, you would probably be correct if you said, I would not be able to tell the difference between those two weights if I lifted them. And you'd be exactly right. Because as it turns out, the just noticeable difference operates in accordance to a ratio. There's Weber. So the key is that this just noticeable difference is not absolute. It changes according to several variables. First off, some people are different than others, and some people can really tell the difference between one thing and another, whereas some people are really lousy at it. Think of like a person who knows how to really taste wine very well. There are some people that are just very good tasters. They can pick up on the faintest of flavors inside a glass of wine. And there are other people that are just like, I don't know, it tastes like wine. It can't really tell the difference between an expensive bottle of wine or a cheap bottle of wine. Also, it varies in accordance to intensity and weight, and this is the most important part of the just noticeable difference. The stronger the control stimulus, the more different the manipulated stimulus must be. Weber, through his experiments, found that our most sensitive uh, area of sensation is vision, and our least sensitive sense is taste. And the just noticeable difference can play out in a equation. The size of the just noticeable difference is directly proportional to the size of the control stimulus. So the equation is delta R over R equals K. Well, what does that mean? Well, down here at the bottom are the labels. Delta R refers to the change of the stimulus, which is the just noticeable difference. And R stands for the strength, weight, or intensity of the control stimulus. And K is the constancy of this ratio for the sense in question. For example, to detect the difference between two weights, if we're talking about weight, the change must be at least 1/50th of the weight. So for small weights, this amount is going to be very small. But for large weights, of course, it increases. What if we're talking to a bodybuilder who lifts heavy amounts of weight, and we put in front of this bodybuilder a 300-pound weight and a 306-pound weight? If we blindfolded the weightlifter, would the weightlifter be able to tell the difference between those two weights? Well, the just noticeable difference would predict that at 306 pounds, that 6-pound difference, which is 1/50th of 300, 50% of the time the weightlifter would be able to tell the difference between those two things. And if you added 7 and 8 and 9 pounds, it'd be far more easy for the weightlifter to detect the difference between the two weights. But if you go under that 306-pound mark and say 304 pounds, the weightlifter will probably not notice the difference in between those two weights at all. Next person we're going to talk about is Hermann von Helmholtz. Helmholtz did a lot of research on vision and color vision in particular. His dates are 1821 through 1904, and he finished his dissertation under Müller at the University of Berlin. Later, von Helmholtz was the professor at the University of Bonn, and then later at the University of Heidelberg. If you've never been to Heidelberg, I highly recommend it. It's a beautiful, wonderful city with a wonderful old university there, before returning to the University of Berlin later in his career. His research team there, believed that mental processes had an observable, measurable neurological basis. So he was definitely a physicalist. He believed that all of our mental processes, from memories to feelings to moods to motivation, all of this had some sort of explainable neurological process, and his goal was to try to measure it. There's von Helmholtz and the Institute of Physics at the University of Berlin. Helmholtz, among his contributions, invented the ophthalmoscope in only 8 days, which allows for direct observation of the retina. This instrument has a mirror that reflects light. Today's ophthalmoscope though they don't reflect light, they just project light directly. But they're very helpful. This is exactly what physicians look at when they look into your eyes. They're looking at the health of your retina. And this is largely what they see when they look through one of those scopes. A very gross picture of the structures of the eye, including blood vessels, the optic disc, and then the fovea in the center, that area of heightened focus where there's lots of cones for color vision. Von Helmholtz believed in the conservation of energy, which was similar to what Isaac Newton had proposed in his laws of motion and thermodynamic theories, etc., and thus rejected this idea of vital or ideal forces. He didn't believe that these things kind of existed outside of our bodies, that they were all contained within a closed system. He believed all energy has a source and it must all go somewhere. Perhaps Helmholtz's most enduring contribution to the field of physiological psychology has to do with his discovery of how fast nerve impulses fire down the length of a nerve fiber. That's really, really cool stuff, especially if you've taken biopsychology. Traditionally, it was believed that spirits or ghosts or something like that flowed through a person's body, and that's what caused people to move and to be in motion. Then after that, people believed, no, it's not that. It's something electrical because we tend to have a lot of muscles that seem to twitch, and we tend to have a lot of instincts. There seems to be like an electrical charge inside of us. And the belief was, if it's true that electricity lives inside of us, then we know that electricity travels at the speed of light, so our nerves must travel at the speed of light. And Helmholtz, upon looking at this question more closely, found, what do you think, faster or slower, or about the same as the speed of light? Well, if you said slower, you're exactly right. The Helmholtz found that our reaction times were far, far, far slower than the speed of light. And he demonstrated this by dissecting a frog leg and looking at the very long and very visible to the naked eye, that's what's key about it, nerve fiber that extended up and down the leg of a frog, and found that there was a major delay between the moment of stimulating that nerve and then the leg actually contracting, as one would expect. So he said there has to be something else going on here. We knew that electricity was part of it, but there had to be something else that was causing this to slow down so much. And Helmholtz discovered it. We are not just electrical people, we are electrical and chemical people. And it's a whole very, very quick series of millions of chemical reactions that slow our nerve responses down to a speed that's way slower than the speed of light. Speed of light is 186,000 miles per second, which is insanely fast. But we, in our bodies, when we have electrical impulses traveling from our brain to our extremities, we travel far more slowly, because for that impulse to get from one point to the other, it has to be patient and wait for several electrical reactions, and several chemical reactions before it can once again discharge. So he discovered also that the harder the mental task, the longer it takes to do it. Now you and I say, well, of course, that's pretty obvious. Isn't that true for everything? The harder the task, if we have to think about something that we've not thought about for a long time, the harder the task, the longer it takes to do it. But when you think about it, that only makes sense now because we've always assumed that to be true. Stop and think about that. Why should that be the case? Why should it be that if something is harder to think about, that it would take longer? I mean, if it's up there in the brain, shouldn't we be able to retrieve that kind of information all at roughly the same speed, regardless if we've seen something once or seen something 100 times? See, this was not known. This kind of stuff we take for granted now because we just assume it's true. But back then, the assumption was that all of this stuff should be happening at about the same speed. And they discovered that, of course, it does not happen at the same speed. Thinking, as it turns out, involves a lot of different reactions, so it's not quick. It involves parallel and distributed mental processing throughout the central nervous system. Therefore, information that we try to think about or try to remember doesn't just arrive in a flash in our minds so that we can then talk about it. Sometimes we have to really work to think about and remember things that we've seen before. It takes the big discovery that Helmholtz made was that these nerves travel, these reaction times for nerves traveled way more slowly than we originally thought, far slower than the speed of light. He also believed that, Helmholtz continuing now, he also believed that cells fire specifically for certain colors. Now this should sound familiar to you because just a few minutes ago we talked about Mueller's specific nerve energy and nerve specificity theory. And Helmholtz's theory, with the help of another researcher named Young, was called the trichromatic, the three colors, theory of color vision. It was published in his Handbook of Physiological Optics. And what he did was he distinguished between the sensation, which is the image that gets projected on our retina of something that we see, and the perception of that particular object. So when we're very young, for example, the things that get projected onto our retina, we really can make very little sense of them. But over time and through habit, we learn that the things that we see are pretty predictable, pretty repetitive, and pretty familiar. So this, our perception, our ability to see things correctly improves over time via trial and error. So this is he was one of the first psychologists to distinguish between sensation and perception. Sensation is when you receive information, perception is when your brain tries to make sense of it. He demonstrated this aspect of vision through experiments that distorted our vision. And what would end up happening is, like, he was one of the first pioneers that would he would force people to wear glasses that would not give them an accurate view of reality. And he found that people's eyes would adjust after a certain period of time to wearing the false glasses that gave you a false lens of reality. And his discoveries really went against this idea that our perceptions reflected reality perfectly or were innate. And it really reflects the idea that the Bible talks about, that there's so much in our heart and in our minds that we can't trust. Sometimes our mind plays tricks on us, and we need to be very careful, and we need to be on the lookout that it doesn't trick us. For example, a lot of people think that if you have a cat, that the world that your cat sees is very similar to the world that you see. But as it turns out, it's quite different. A cat will have vision that looks something like this. According to some researchers, this is what a cat sees in terms of its retina compared to humans. So the top view would be what humans see. The bottom view seems to be what cats see. The only problem with this theory is that it assumes that cats' vision doesn't change either, and of course we now know that a cat's vision does change. Here's the stereoscope. Helmholtz invented the stereoscope, which showed that two identical images viewed from different angles could be shown in 3D. So after a period of adjustment, the pictures start to blend, and our brains start to form 3D images of what it is that we're looking at. The key to the stereoscope is that when you're first looking at it, you don't see in 3D. You see two kind of blurred images that look like slightly different takes of the same picture. But after a while, our brains adjust and we see a 3D picture. And this was kind of a big novelty item, kind of a big sensation that people looked at. Last person we're going to look at for our lecture today is Gustav Fechner. Fechner's dates are 1801 through 1887, so everybody's kind of around the same time in this era leading up to the first psychological laboratory with Wilhelm Wundt. Fechner sought to prove that all living things were composed of both matter and soul. Now, he didn't do a very good job of it because it's really hard to prove that the soul exists. But because he did such a good job in his experiments, it paved the way for a lot of philosophers and physiologists to start asking questions of a psychological nature. Fechner was also at the University of Leipzig, and he had a really creative streak in him, and he was prone to big bursts of energy, and he really got the ball rolling for someone like Wilhelm Wundt later on to come on and pick up where he had left off. Fechner wanted to establish a connection between the strength of a stimulus and the strength of a sense response. Again, this idea was eventually rejected by Mueller, but how to do this? After all, sensations are subjective. Well, what he did was he came up with the answer around the same time as Weber as the just noticeable difference. He said, use these as a guideline. The just noticeable difference ratios aren't perfect, but they do provide us with some kind of a reliable way of looking at how to tell the differences between these two things. So to this day, Weber's law and Fechner's law are used almost interchangeably to describe the same thing. Fechner believed that every increase in a just noticeable difference is the result of increasingly multiplying a stimulus by a fixed constant. So for example, if we do 1 times 3, then a person is going to perceive the stimulus as being twice as strong. But if you do 1 times 3 times 3, it'll be 3 times as strong. 1 times 3 times 3 times 3 will cause people to perceive a stimulus as being 4 times as strong. The equation here is S equals K log R. This equation basically is another way of looking at Weber's law. You basically come up with the same thing. The idea that the just noticeable difference is a ratio of the differences between two weights, and the just noticeable difference gets bigger as the stimulus itself gets bigger. So his methods looked a little bit different than Weber's. What he did was he would increase the amount of a stimulus until it became perceptible to a human being, like a small flicker of light. And then he would introduce a constant stimulus, and he would test the average of the strength of the stimulus that is perceived by the subjects to be either present or dissimilar. And then he would test the amount of error that happened when a subject was asked to adjust the stimulus to match the answer. And the answer, the amount that they adjusted, turned out to be the just noticeable difference. Now, he did have a problem. He believed that all just noticeable differences were created equal. This is not true. But he did believe that we could measure mental states. This is one of the guiding principles of the early psychologists. In fact, several years later, William James said, if we could one day get to the point when we could take a person's mental state and see perfectly clearly a brain state that corresponded to it or caused it, that would be the scientific achievement. But we still have not achieved that. So with Fechner, the key here, like it is with these other people, is not necessarily to evaluate how right or how wrong he was, but in all of these researchers and their commitment to measurement. And so we've finally reached the point at which we can leave the world of philosophy and leave a little bit the world of pure physiology and now turn to Wilhelm Wundt and the world of psychology.